So imagine that you had one function, say a trigonometric function like this red one here, and you had a cubic function like this neat little blue one right here. Let's say you wanted to connect them at a specific point and you wanted where they connect to have equal gradients. It was a smooth ride from this point to this point. How could you go about that? Okay, well, first of all, you definitely need to know the equation of one of these functions. Because of my big brain and my knowledge of periodic functions, I know that this equation is 2 sine pi on 6x plus 5. I know that because the amplitude is 2, it's been shifted up by 5 units, period equals 2 pi over b, and the period here is 12. So I solved that to get pi on 6. Alright, I know the equation of the periodic function. I don't know the equation of this blue function, and it's important kind of that I don't know the equation of that cubic function, but we know that all cubic functions take the form of ax cubed plus bx squared plus cx plus d. And if I could only figure out the a, b, c and d values, I would know the equation of that. So that's what we're trying to do. Alright, so this is actually future Joel, just mentioning that in this particular instance I'm working with a cubic, so I'm working with ax cubed plus bx squared plus cx plus d. But I can do anything if I'm trying to connect any function to any other function. I just need to write its general form. For instance, if I already had a cubic and I was trying to connect a trigonometric function to it, then the general form of that trigonometric function would be a sine bx plus c plus d. Or if I already had a cubic and I was trying to connect a quadratic to it, then the standard form would be ax squared plus bx plus c. Or if I already had a, let's say, well, let's go with, if I already had a trig function and I was trying to connect an exponential function to it, again, some sort of standard form, ae bx plus c plus d, those would be my sort of standard forms if I was trying to connect one function to another function, and then I'm trying to find those a, b, c and d values. Okay, back to past Joel, who was trying to figure out that question that we started with. That's 4 unknowns, which is like a lot, which means that we're going to need to know quite a few points or ideas or facts about this equation. And one of the facts I know about this equation is it needs to meet this red function at wherever that point is there. So I wonder if I sub x equals 19 into the red function, what is that point right there? Turns out that when you sub 19 into this equation, you get the number 4. Now I'm not going to show you how to do that. I did it because I was feeling lazy. I jumped into GeoGebra, I had the equation of the line there, and I just plotted a point on it. Turns out it was 19.4. A graphics calculator could do the same kind of job with like a Y-calc, I think is usually what they're called. Or you could just type into your calculator 2 sine pi on 6, 19 plus 5, 4. My point is that we know that that point there is 19.4. And importantly, we know that this equation here must pass through the point 19.4. So that means we can sub in 4 for g of x and sub in 19 everywhere where we see x. A little bit like that. Now, of course, we can simplify that. So this is gold because this is our first equation. Our first equation with no x and y in it, just the a, b, c, and d, which are the 4 variables that we want to know. Alright, so not only does this equation need to meet that trig function at point 19.4, but it also needs to have the same gradient. So, what is the gradient of the trig function at point 19.4? Well, for that, we're going to need the derivative of that function, which you should be able to find. There's the derivative. You can always check that on a calculator or something, but I know that that's a derivative. Now, I want to know the gradient at a particular point when x equals 19. So if I sub 19 for x here, I'll get a value. I'll admit I was hoping for a nicer value than that, but that's what it is. I've kept heaps of decimal points because I'm trying to get a very accurate picture of this meeting at the same point with the same gradient. Okay. Now, not only do we now need to know what that gradient is, but we need to say, okay, I want this gradient at that point to be the same. So, first off, we need a derivative function for that blue function, right? So we're going to have to find the derivative of g of x. Now, that can be a little tricky for people because of these variables here. So I will run through that one. G dash of x equals 3ax squared. Remember that a is just a number. It's not, then 2bx. Then cx, so if it was 5x it would be 5, so if it's cx it's just c. And then that d disappears. Now, we know that at point 19, when x is equal to 19, we want the gradient to be equal to that, because the trig gradient's equal to that. Subbing in negative 0.906, etc. for the gradient, and subbing in 19 for the x value, I get this equation here in terms of a, b, and c. That is my second equation. Now you might be thinking, well, this equation has a d in it, this one does not. Is that going to be a problem? This one just has a 0 coefficient in front of the d value. So we still have two equations in 4 variables. Okay, so now we just need 2 more equations, because if we've got 4 variables, we need 4 equations, or we're not going to be able to solve them simultaneously. So where am I going to find those? Well, I've got to go back up here now. All I really need to do here is pick 2 points on the blue equation that I want it to pass through, right? Remember, I kind of sketched this one by hand, so I can pick the points that I want it to pass through. And I want it to pass through this point here, which we'll call 24, 2. And I want it to pass through this point here, which we'll call 21.5, 4. Now, these aren't precise, but again, I'm choosing those points to be the ones that my equation is going to pass through. So now I'm just going to sub in 21.54 into g of x. I get that. When I do that, I get this pretty ugly looking equation here. But importantly, it's our third equation. It's got an a value, a b value, a c value, and a d value. Okay, and I'm also going to sub in the point 24.2 into g of x. Okay, that's looking good. 2 equals blah, 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 blah. And there is my fourth equation. So now that I have 4 equations and 4 variables, I can go into my calculator, click equation. Yours will be different, but what we're doing is solving simultaneous equations. So here, I'm going to use simultaneous equations, 4 unknowns. Now, I've actually already entered all the data in here. So if I show you what my first equation is, I've actually entered the fourth one in first. 13824 is the first value, 576 is the second value, 24, D, 1D value there, and then across equals 2. So the way that this is set up tells you how to set it up here, but the thing that the equation is equal to needs to be on the far side. The only interesting thing here maybe is for this equation, I had to do 1083, 38 for the B value, 1 for the C value, and 0 for the D value because there's none there, and then that negative 906. Now it looks like it's rounded there, but you can see I've entered the whole thing. It's going to be so important that you use like 100 digits here, as many digits as you can, because small, very, very small changes in polynomials change their shape significantly. Okay, solve, and we get this here. Now, don't enter this value for your equation. Enter this value for your equation. If you enter this value for your equation, It's never going to work. This value, it'll line up. It looks ridiculous, but this is my final answer. What is that answer? It's a blue cubic that meets the red trigonometric function at 0.194, because that's what I had there, with the same gradient at 0.194, that's why this equation was here, and passes through this point and this point, 2 points that I've chosen. Now, does it work? It's the question you've got to ask yourself, and you've always got technology, so you can always check these things out. This was my initial goal, a trigonometric function, then a function that meets it at 19.4. Here is the purple function you're looking at there is the big, long function that I've created. You can note I've put in all the decimal places. Because if it looks like I'm a bit more stressed than when I started the video, it's because this video's had some stops and starts because I was being lazy and not entering enough decimals. Disaster. So, let's really zoom in here, right into here. You can see, just by eyeballing it, that graph is coming in and just touching at that point. Those gradients are matching up. Now, of course, we don't have to just eyeball it. We can zoom out on that. GeoGebra is quite nice because it'll give us some tangents. So let's click tangent. Tangent to the purple curve at the point F. Negative 0.9069. All right, so that's the gradient of that black line that I've just created. And now let's do a tangent to the red curve at that point as well. Negative 0.9068 ... You can see a small error there. They don't quite match. Because we've been doing rounding here, even though we've been working really, really hard, at the 10th decimal place, which is where I stop putting decimal places in, they stop lining up exactly. You can see they sort of stop, they probably stop lining up about here. But that's a bit of a limitation, I guess. But that's no big deal. Okay, you can see also that this purple curve passes through those other points that we talked about. 24.2, I think it was 21.54. It's passing through those points as well. You can test that. You know, there's nothing stopping you now that you've got a function, this blue function here, adding a third function onto the blue function and adding a fourth function onto that third function, essentially through going through this same process. But that is how I would join two functions so that their gradients match.